welcome all of you. So, previously we started with life cycle assessment and completed the first phase of LCA, that is goal and scope definition. Now, in today's lecture we will cover the remaining 3 phases, that is the phase 2 of life cycle inventory, phase 3 life cycle impact assessment and phase 4 interpretation of results. So, that is the overall LCA framework with 4 phases, where you see all of them are interconnected, interdependent, linked to each other, and life cycle inventory. So, once the goal and scope is defined, the second phase of life cycle assessment is life cycle inventory, where there is a lot of data collection, all the inputs and outputs in terms of material and energy. Outputs can be emissions, waste, losses, products, okay, of a product system are quantified and compiled. So, they are not just like quantified, but they need to be compiled properly in the form of inventory tables. And if they are to be understood by the user properly, they need to be properly classified separately also, like all the mass values separate column, energy values separate column, okay. The emission factors, all those things need to be compiled systematically, and that will give us a complete environmental flow data set, which will be used for the phase 3, which is the life cycle impact assessment. So, this life cycle inventory is a very important phase, and all the results would rely on how effectively and reliably this inventory data was compiled. It is also called inventory analysis. It is a time consuming process. If we have to do LCA for existing system, for existing industry, we need to know the mass and energy, the input and output for the entire process in the system, and there will be a lot of data which should be available. But if on the output side, for let us say for emissions, for waste, if the measurements are not proper and the data is not available, then those measurements will need to be taken. So, it is a time consuming process. Also, sometimes for proposing a new system or a modification in existing system, prior to setting up some equipment, if LCA needs to be done, then lot of literature review, surveys, contacting industries or other people who have used similar technologies, that would take a lot of time to gather the data. And once, even after doing all these activities, if the data is gathered, it can be modified or changed, because this life cycle inventory is a iterative process. As the model goes on improving, we may realize that some additional data is required which is missing. So, those additional data will need to be discovered and need to be collected again and added to the inventory table. So, the key steps involved in this second phase of LCA, that is LCI life cycle inventory, is first is collect data, gather all the input and output for each process, for each activity or the unit operation or the block in the entire system within the system boundary. Model those processes. You can build the process flow diagrams and link unit operations like sequentially. So, what happens, like if we have 10 unit operations one after other, so the output of one can become the input of other block. The output of second block will be the input for third block, and then there may be some additional inputs and outputs coming out of each blocks, okay. So, if we have the proper process flow diagram, it will help us like reducing errors or mistakes related to double counting or multiple accounting of the same data flows, okay. So, the second step is model the processes using proper flow diagrams and linking of unit operations. Then quantify these flows. Each of these flows you need to have the numerical value. So, you quantify those flows and convert all the materials, energy, emissions into a measurable units preferably, and link it to the functional unit, okay. Or it is not possible to have all these measurements in the single unit, but irrespective of the units, like if it is in kg, if it is in megajoule, and if these are in say again kg or like just ppm, and the functional unit is like say 1 kilowatt hour if it is for electricity. So, all these things should be able to be correlated in like kg per kilowatt hour, megajoule per kilowatt hour output, kg or ppm per kilowatt hour output. That is how you quantify all the flows and link it to the function unit. Then apply allocation. If you remember, in scope, goal and scope stage, in the scoping phase, we just decide the allocation procedure. We do not apply it, we just decide whether allocation will be done on the mass basis, energy basis or mixed basis, and in the life cycle inventory, we apply the allocation for inputs and outputs wherever there are multiple output. So far as research papers and studies are concerned, researchers suggest to avoid this allocation if possible, and that can be done by considering those other products as the unwanted products and just cut down the emissions related to those products within the system and try to avoid the allocation. But if it is not possible to avoid allocation, it is fine to use this allocation procedures and give the weightages to the different outputs or inputs coming from the multi-output processes. Once all these things are done, you compile and check the data quality to ensure that the inventory table is complete, consistent and accurate or reliable. So, all these 4-5 steps will end up giving a reliable or a correct life cycle inventory table. Let us take one example of say 1 cup of tea or just 1 cup of black tea using LPG stove. So, if this is the process making 1 cup, that is 150 ml is the approximate volume. So, that is the unit process. What would be the inputs going to the black tea? Just water, tea powder and some LPG to provide heating, and outputs would be the final tea, some CO2 because we are combusting LPG in the burner, the used tea powder and some steam because some water vapor would be like released to the environment while the water is boiling while making the tea. So, if you have to quantify this LCI data in the form of a table, how it would look like? These are some approximate assumed numbers. You can have your own numbers and a own separate case study also. So, these are the flow type where water, tea, LPG, some CO2 emissions, used tea powder and steam loss, and based on in what unit these can be measured, you can see the quantities. Like water, it is measured in volume, liters, rest things are measured in the mass. Like CO2 emission is taken from the combustion like emission factor for LPG. So, if we know that for boiling 150 ml water for 5 minutes or 10 minutes, 5 gram LPG is going to be consumed, that is the amount of CO2 emissions it will release. Then some used tea powder, that is organic waste, and some evaporated water which leads to the steam loss. So, that is how the LCI data will look like for 1 cup of tea. So, now you have all the inputs and outputs going into the process. But if you see carefully, for making 1 cup of tea, there are many other things which are also required. Okay. So, if we have to burn LPG, we would need a burner for it, we would need a lighter for it. To screen the tea, we would need a screen, then we would need this cutleries to serve the tea, or else the purpose will not be served unless the system boundary for making this tea is just the process of making tea. Okay. So, the question is, does life cycle inventory account for this kind of equipment or not? Because if this equipment is not there, it will not be possible to make tea. So, the answer is both yes and no. We can account equipment in certain cases, and in certain cases we do not need to account for equipment. So, in most routine LCAs, equipment like boilers, stoves, reactors, machines which have like long life of 10 years, 20 years, 30 years, these are not included because its contribution per function unit is negligible, usually very small. Okay. Then the data on equipment manufacturing is very difficult to obtain from the suppliers or manufacturers. It will be a very tedious and long time consuming process. And ISO 14044, the guidelines which tell us how to do LCA, they allow exclusion of capital goods if impacts are negligible. So, in most of the LCAs, you will not see these equipments being included in the inventory list, but the equipment need to be included in LCI in certain cases when equipment is energy intensive or material intensive. For example, solar panels, if we are talking about doing LCA for solar PV plant or a rooftop solar PV, then those panels need to be properly maintained, purchased, life may be shorter, they may get damaged. So, this wind turbine, solar panel, EV batteries, the small reactors, they are very energy intensive, very material intensive, and because of high pressure, high temperature operations, they may get replaced soon. So, in that case equipment is included. If equipment is short lived or frequently replaced, then we need to include the equipment in LCI. Also, it depends on the goal or the type of LCA that we are doing. If we are looking for cradle to grave analysis, there we typically try to use the equipment, but again there also we may exclude equipment if the contribution per function unit is negligible. So, that is about the equipment or capital goods included in life cycle inventory. That is third phase, like till second phase we have all the data. First phase, it was goal and scope, define what is the purpose, why we want to do this LCA, for whom, the system boundary. Okay. Now, the second stage was collected all the data. Now, once all the data is there, you can actually start calculating the impact. So, third stage is the actual core of LCA or the rewarding part of LCA, which will give us the environmental impact of different activities or products. It identifies and evaluates the amount and significance of the potential environmental impacts arising from the life cycle inventory. So, since all the inputs and outputs would be compiled in the life cycle inventory table, we would be focused mainly on calculating the impacts from that table. And in common LCIA, like the life cycle impact assessment methods, there are two main approaches which are used to classify and characterize the impacts. One is the problem oriented approach, which we also call as midpoint approach or midpoint indicators, and damage oriented approach, which is also called as endpoint impact category or endpoint approaches or endpoint categories. Okay. Once we see what is characterization and classification, we will also see what are different midpoint indicators and what are different endpoint indicators. For any process, right at the point of that process happening, we always calculate the midpoint impact categories, and this damage oriented approach is, it happens towards the end and at very far from that production or from that problem point. Okay. And this damage would be mostly either on the human health or on the environmental components ecosystem or on the resource depletion. So, it is like the end effect which can be observed as a damage, but midpoint indicators would be the environmental impacts that are happening right there near the source of the problem. So, the key steps involved in life cycle impact assessment, there are 3 steps. First is selection of impact categories and indicators. So, impact categories would be selected based on what environmental problems we need to study. If it is a power plant running on fossil fuel, obviously the climate change, acidification, eutrophication, these would be the areas of prime concern which needs to be identified. If it is a rice mill or like say farming or agricultural activity, something related to toxicity, soil, land use amendment, human toxicity because of use of pesticides, those would be the important parameters more than climate change or global warming potential. So, based on, so first you identify which environmental problems are of importance to us depending on the system, and based on that you choose the impact categories, the indicators and the LCIA method, the life cycle impact assessment method, whether we are going to use the Excel sheet provided by CML or the recipe method which has like 16 to 18 midpoint indicators and 3-4 endpoint indicators, or TRACI or some other method. And this choice of methods would be based on the region, goal and data availability. So, the data sets available in different LCA softwares for different regions, that will also be a basis for choosing a impact category, indicator and the LCIA method. Once these impact categories are identified, the indicators are identified, these indicators will have some units also, those units are finalized. Second step is classification. Each elementary flow from inventory table, whether it is an emission or resource, does not matter, each elementary flow should be assigned to one or more impact categories based on the type of impact they contribute to. For example, CO2, methane and N2, these are greenhouse gases. So, they would definitely contribute to climate change. They may not contribute to acidification or eutrophication potential. Okay. So, if we in the inventory table, if you have these values of CO2, methane, N2O, SO2, NOx, SOx, all those emissions are given to you, we have to understand, know that which of the elementary flows are responsible for which of the environmental impacts. So, if climate change, acidification, eutrophication, these are the midpoint impact categories, then the concerned contributors from LCI, that is inventory table, needs to be assigned to each of those impact categories. So, for example, if we can assign these gases to climate change or global warming, these ones can go to acidification. If there is like say PM 2.5, PM 10 measurements, they can go to the smog formation or particulate matter formation. So, in the first step where we discussed about midpoint and endpoint categories, so what is the difference? Okay. But before I cover this, let me cover the next slide, which shows you how they can be connected. So, this is the life cycle inventory taken from one of the research papers. You have the list of all these gases or chemicals or emissions and activities or the inventory data. And now, each of these can be linked to different midpoint impact category. Midpoint impact categories are those which are, and I think these are mainly as per the recipe methodology: particulate matter, ozone, radiation, human toxicity, global warming, water use. So, these are midpoint impact categories. Now, because of this, actually because of this life cycle inventory, there is a potential impact caused by each of these inventory flows, and now these impact categories measure that potential impact. Now, once that impact happens, it will damage the human health, ecosystem or resource availability. But now these are very broad areas: human health, ecosystem and resource availability. So, in human health, which specific aspects, what would be the pathway of the damage, whether it is a respiratory disease or cancer or malnutrition, that sets the damage pathway. So, midpoint impact category leads to endpoint damages through certain pathways, and those are called damage pathways. So, midpoint impacts contribute to endpoint damages. For example, particulate matter and ozone formation will lead to respiratory disease, which will have damage on human health. Similarly, ecotoxicity or eutrophication will damage freshwater species and it can damage ecosystem. Mineral toxicity or depletion of fossil resources will have added cost, which can damage the resource availability. Okay. So, that is how life cycle inventory is connected to life cycle impact assessment. And if there are two types of categories we are talking about, midpoint impact and the endpoint area, and they are connected through the damage pathways. So, what is the difference between these two categories? Midpoint impact category, it is intermediate environmental problems caused by emissions or use of resource, whereas endpoint impact, it is the final damage to the parts of the components of the environment, which is human health, ecosystem and resources majorly. Midpoint impact category, it occurs in the earlier stage of the process, which is closer to the emission point, closer to the source of the problem. Endpoint impact category, it is happening at later stage, it is realized at the later stage, it is closer to the real world consequences. For example, if we take example of stubble burning in farms, the local smog or smoke can be considered as a midpoint, which is very close to the emission site, but collection of aerosols like 100 km far, or acid rains or smog formation like 100 km far at later stage, can be considered as a endpoint impact category. Purpose of midpoint impact category is to quantify potential impacts such as climate change, toxicity, acidification, eutrophication, ozone depletion, particulate formation, carcinogenic emissions. So, all these are estimated here by midpoint impact categories, and purpose of endpoint impact is to quantify final damage such as loss of species, the costing of resources which are getting depleted, or the cost or price of this human health damage. Examples, those all these things we have seen already, and human health, ecosystem, resource scarcity, these are the three major damages which are considered in endpoint impact categories. So, midpoint category are related to different measurements or the aspects of the environment, but more than aspect of the environment, I would say aspect of the activity which is going to have impact on environment. Okay. And indicator is a term in which these impacts would be quantified. Because it is a term which quantifies this midpoint category impacts, these indicators will have a certain unit, and the unit for each of these indicators is constant, and each of these indicators may have different contributors. Like global warming potential, it can be due to different greenhouse gases, it can be CO2, methane, N2O, okay, SF6, chlorofluorocarbons. So, all those greenhouse gases can contribute to global warming potential. This 100 stands for 100 year of time reference. So, now the measurements of these gases emissions can be in one unit or can be in different units, but to convert it into the unit of indicator, which is a standard like kg CO2 equivalent, there would be some factors given, characterization factors given, like 1 kg methane is equal to 25 kg CO2 equivalent in terms of global warming potential. Okay. 1 kg, 1 N2O would be something around 300 kg CO2 equivalent. So, that conversion factors can be used, and each of these gaseous measurements can be converted to CO2 equivalent. So, it is easy for comparison. Similarly, ozone depletion has unit. So, each of these midpoint categories have different units. Similarly, endpoint area, health, ecosystem and resource, the indicator can be disability adjusted life years. The unit will be the years of life lost, like how much is the life which is declined. Species loss or per species year, that is the unit would be just species lost or species year. Additional extraction cost can be in dollar or in terms of energy. If it is fuel, we can say this much megajoule is lost. So, that is how each category of midpoint or endpoint will have certain indicator, and each indicator will have a fixed unit for fair comparison. So, just revising the key steps. The first was selection of impact categories and indicators. Second was classification of the data given in the inventory table to specific categories. Okay. The third is characterization. Each flow is multiplied by a characterization factor so that it can be expressed in a common unit per category. That is what I told earlier, like methane, CO2 and carbon monoxide or N2O can be converted to kg CO2 equivalent. Let us take one example. So, if you have to estimate the climate change impact, it is a midpoint impact category, indicator is global warming potential GWP 100. If we have two gases CO2 and methane, where 5 kg and 0.2 kg is the emission. Characterization factor here, 1 kg CO2 is 1 kg CO2 equivalent, straightforward. But for 1 kg methane, the value ranges between 25 to 30, let us take 28. So, what would be the final impact by, if the process is emitting 5 kg CO2, the impact it is 5 kg CO2 equivalent for CO2. For methane, it will be 0.2 into 28. So, 28 into 256, 5.6. Okay. So, you see now, since both the units or the two different entries in the inventory table and their impact are calculated or estimated in a same unit. So, now we can actually add them. Okay. So, 5 plus 5.6 will give us the total global warming potential, which is 10.6 kg CO2 per equivalent. Similarly, for just to explain, I took just two gases, we can have multiple more number of gases. If characterization factor is given to us or is obtained from literature, we can find the impact of all those gases in a single unit. So, that if we add them, we get one final value for that one impact category. Second example, let us take of acidification potential. So, mainly by sulfuric acid, nitric acid, these are the two primary acid resulting in acid rains. So, the substance which cause them are the oxides of sulfur and nitrogen. So, if we have the measurement of SO2 and NOx as 0.05 and 0.02 in kg, and characterization factor, since acidification potential standard unit is kg SO2 equivalent. So, all the measurements, the third gas which can be here may be related to hydrochloric acid, HCl, okay, the chlorine based substance, can also be converted to SO2 by using certain characterization factor. So, 1 kg SO2 is 1 kg characterization factor, but for NOx it is 0.7. So, the total impact for SO2 for 0.05 kg, it is 0.05 into 1, 0.05, 0.02 into 7, it will be 7 to the 14, 0.014. If you add this, you will get total acidification potential in kg SO2 equivalent. So, this is your inventory table. These values come from the life cycle inventory table. Now, when you have to calculate the life cycle impact or you have to do the impact assessment, you need characterization factors, because these characterization factors will bring down each of these measurements to a common unit, so that final impact can be obtained by simply addition of those values. So, similarly, it can be done for each of the midpoint impact category, so that we have climate change, acidification, eutrophication, all those impacts listed for one process or for multiple processes, depending on how much data we have it in the life cycle inventory. So, fourth step, okay, that was the third step, right. So, if we revise quickly, first step was selection of impact category and indicators, second was classification, third characterization, and fourth is the optional LCIA steps. These are not mandatory in ISO standards, but are often used to help interpretation stage. Like those, some of the optional steps are like normalization, grouping, and weighting. Okay. Since there are so many impact categories like say 16 or 18, it's difficult to tell like overall which of the alternatives is performing better overall. If we have, then we will have to compare for all those 17 and take some average or do some clubbing of it. So, for that these steps are there. One is normalization. So, you compare impact results to a reference value. For example, if one product emits 5 kg CO2 equivalent, and if in that region there are like say 100 people, huge population, and per capita emission is 2000 kg CO2 equivalent, maybe this is per capita annual emission. Okay. So, there is a product which emits 5 kg and per capita it is 2000 kg CO2 emission, depending on the number of people using it for 1 year using different amounts of products. Okay. So, the normalized value on the basis of person equivalent will be 5 by 2000, that is 0.0025. So, if we try to normalize it based on number of people or total consumption of the product, then it will be easy to compare rather than just looking at 5 kg and 2000 kg. It is difficult to compare, but when we say 0.0025 person equivalent, that gives the normalized value and it will be easy for comparison. Grouping, categorize impact categories into themes or priority groups. For example, if we are dealing with air related impacts, climate change, acidification, ozone depletion or particulate matter formation can be considered under air related impacts, all can be grouped together. And if we are focusing on water related impacts, we can group water use, ecotoxicity, eutrophication under one group. And if we just take the addition or average of those, the impacts in under those groups, we can tell water related impacts. And if we have these two values, air related impacts, water related impacts, it will be easy to interpret and convey the results that more efforts are needed on the water side or on the air side. The last is weighting. Assign weights to impact categories based on importance. Again, now this clearly depends on the purpose of LCA and the target audience. If the LCA is being done to get the environmental compliance or to show that we care about the environment, then the climate change would be given the higher weightage compared to human toxicity, eutrophication, resource depletion, because higher weight means the final score would be influenced more by that particular category. Okay, if we have higher weightage to climate change, the entire results, the final collective results will be influenced more by the climate change category. So, that is how the weighting is done. These are not the mandatory steps, but they are often used in different LCA studies. Let us take one example here for life cycle impact assessment. So, these are some LCA like inventory data, you have emissions to air, emissions to water, there are these gases, and these are some phosphates and ammonia. So, impact categories identified are global warming potential, acidification and eutrophication potential. So, we classify. In classification, what did we do? We connected the concerned life cycle inventory to the concerned impact category. So, out of all these gases, these 3 contributes to global warming, these 3 contributes to acidification potential, these 2 contributes to eutrophication potential. One of these gases, NOx, also contribute to eutrophication potential. So, that is there. So, it is possible single data in an inventory may contribute to multiple impact categories. Okay. It's not like the straightforward case that one entry in the inventory table will contribute to only one impact category. It is possible that one entry can contribute to multiple impact categories. Now, once this classification and impact category listing is done, we have the characterization factors given for each. So, for CO2, for CO and methane, the factor is 1, 3 and 25 in terms of kg CO2 equivalent. Here for acidification, we have 1, 0.7 and 0.88. It is given here, okay, 1, 0.7 and 0.88. For ammonia, it is 0.33 and 0.13, and for converting everything to phosphate. So, global warming potential is measured in kg CO2 equivalent, acidification potential measured in kg SO2 equivalent, and eutrophication potential measured in kg phosphate equivalent. The characterization factors for the entire data are known to us. Okay. Now, if you just do the simple multiplication and addition, you should get these numbers. For example, let us do 1. So, 1.3 is the CO2. So, we will have 1.3 plus 3 kg CO, and impact factor is the characterization factor is 3. So, 3 into 3 9 plus 6 kg methane, okay, and methane's global warming factor is 25. It can be anything between 25 to 30. So, here it is 25. Previously in one example we had taken 28, right. So, 6 into 25 150. So, that it comes out to be 160.3, and the units of all 3 are kg CO2 equivalent. So, that is how it will match. For this one where this NOx had contribution in both, so we use the entire quantity there. For SO2 it was 1 into 0.001, NOx it is what is say 0.08, and then it is 0.9. Similarly, for eutrophication potential you use 0.08 kg NOx, 2 kg phosphate and 0.1 kg ammonia using this factor. So, we are not doing allocation here that out of 0.08 kg NOx 50% will go contribute to global warming, or 50% will contribute to eutrophication potential, or 50% will go to acid. We take the entire amount and try to calculate the impact assessment, because these impacts need not be happening. These are the potential impacts that may happen, that we are calculating based on the data and the characterization factor, okay, that we have to understand. Let us take one more example, the last one. If we have to do the impact assessment for comparison purpose, let us say 1 kg plastic versus 1 kg paper used for packaging. These are some assumed numbers for different flows. For plastic and paper 1 kg, you have CO2, methane, SO2, NOx, phosphate, and these are all the units are in the mass basis. So, if you have to calculate the climate change potential for global warming potential, that is in hundreds for plastic and paper. So, everything has to be converted to CO2, right. So, for methane the characterization factor is, let us say 28, and for there is no other gas which is contributing to global warming potential. So, we need only CO2 and methane. So, this 2 into 1 plus 0.03 into 28, that gives us climate change potential or global warming potential for plastic, and these two numbers will give us for paper. So, what is better in terms of climate change impact category? Paper is better than plastic because it has low emission value or the low global warming potential. Second, let us check on acidification. Plastic, again for acidification it is mainly SO2, and I think it is the NOx, SOx and NOx, they are responsible, and this phosphate would be for eutrophication. Okay. So, 0.01, 0.02, and the characterization factor here is 0.7 to convert NOx into SO2 equivalent. Okay. So, for plastic it is 0.02, For paper it is 0.04. If we compare only on the basis of acidification potential, which is better? Plastic is better. So, in one impact category, paper is better than plastic. In other impact category, plastic is better than paper. So, which one is better overall? It's difficult, right? Let's look at third impact category, eutrophication. Based on the data, it's only phosphate which is going to water, and water bodies typically get eutrophicated. So, we use only this value. So, which one is having higher eutrophication? Paper. So, which one is better basically? Again, plastic is better. So, now plastic is better in two categories. Now, since this example we are restricting only to 3 categories. Okay. So, out of 3, in 2 of the categories plastic is better than paper, and in one category paper is better than plastic. So, can we say overall plastic is a better option for packaging? Let us look at, these are 3 impact categories that we see: paper, plastic, better option. Okay. Universally neither plastic nor paper is better, because each of them performs better in individual or different impact categories. But if ever we come across this kind of situation, we would go with the product or with the alternative which performs better in the maximum number of categories. But that will be on the basis of the assumption that each of the impact categories are equally important to us. Understood? So, here plastics may be better overall because it is performing better in 2 cases, 2 categories instead out of total 3 categories. But suppose if the importance or weightage to the global warming potential is significantly higher than acidification and eutrophication potential, then paper may also turn out to be better overall, even though it is better only in one of the categories. Understood? So, final results would depend on these weightages. That is why the 4th step which I showed for life cycle impact assessment, which are not mandatory, which deals with normalization, grouping or weightages, it becomes important in the real world scenarios, because if our major concern is climate change for certain industry or certain case study compared to acidification or eutrophication potential, then in spite of being better only in one of the impact categories, overall better option would be paper for us compared to plastic. So, that is why universally better or all time best option choosing, it is not possible here. Everything would depend on the context and the importance of the categories with respect to the what we say project proposer or the LCA expert who is conducting the LCA, right. So, I think that completes the phase 3 of life cycle assessment. The final phase, after these 3 phases are done, and the goal and scope, life cycle inventory and impact assessment, the final phase is interpretation, where the results from earlier 2 phases, that is life cycle inventory and impact assessment, these results would be analyzed, checked and converted into the form of clear conclusions and recommendations, because it is interpretations which will help policymakers or industry people or those who are getting this LCA conducted to make decisions. So, based on these results, they need some clear conclusions and recommendations, and this interpretation, as if you recall that LCA framework picture where all 3 phases were linked with a big block of interpretation having both side arrows. So, it is a continuously ongoing during assessment and it helps to guide other phases. It can be modeled as conclusion and recommendations to the decision maker, and it should be consistent and based on the goal and scope of the study. So, whatever interpretations we do, every time the goal and scope has to be kept in mind. It's just like writing a PhD thesis. If you have a title of your PhD thesis, nothing in any of the chapters in the thesis should go delineating from the title of the thesis. So, the interpretation has to be based on the goal and scope. It should reflect the uncertainties which are inherent in LCA, and though it is a fact that LCA is a relative approach and uses some function unit based on a lot of data, and the impacts are potential and not actual, because it is all calculation based. We make certain assumptions, we set the system boundary, we use some characterization factors from literature. Sometimes we do measure the data, but many times we take it from references or other similar industries. So, it is a relative approach, it is a theoretical approach. So, there are a lot of uncertainties, but those uncertainties can be addressed in the interpretation stage. So, just to summarize the interpretation phase, because there is no calculations, no mathematical calculations involved in interpretation, it is just the overviewing, overseeing and analyzing of results. So, in one word or one line definition, it is analyze, check and conclude the LCA results, based on which decisions would be supported or based. And it is this phase which links LCA results to decision making, and it provides generally in three forms. One, conclusion form, which option is environmentally preferable, or what is the total environmental impact of a given option or a given system. Limitations, the gaps in the data, the assumptions, uncertainties would be described under the category of limitations. The conclusions will tell us which option is best or what is the total emissions. Limitations will tell us what is the flaw or gaps in the methodology, what are the uncertainties, what were the assumptions made, why, whether they are acceptable or not. And recommendations would be how, once the impact is known, how and where to improve the process, design or material, so that the impacts are reduced or within the acceptable limits. So, with that I think we will summarize today's lecture. We started with the phase 2 of life cycle inventory, which deals with the collection of data, like mainly the inputs and outputs in the form of material, energy, and each of those inputs outputs are linked to the flows and represented in the form of table. Phase 3 is life cycle impact assessment, where classify the inventory, we do the characterization factors and then estimate the environmental impact, group it into the midpoint impact categories or the endpoint damage categories, and do the overall calculations. Interpretation is the final phase, which validates or analyzes and makes some conclusions and recommendations based on the results of life cycle inventory and life cycle impact assessment. So, that completes the 4 phases of life cycle assessment. Thank you.